In the previous module 5.1, we looked at different types of horizontal heat exchangers and effect of soil thermal parameters. In this presentation, we'll focus on more the design aspects, the design methodology of horizontal ground heat exchangers. As we showed in the previous presentation, we can distinguish several types of ground heat exchangers. The most well-known are horizontal, slinky or ring collectors, and spiral type of heat exchangers, and we'll consider each of those in these presentations. As with any ground heat exchanger, the design calculation should include the thermal response of the soil itself and interaction between adjacent ground heat exchangers. We should consider the fluid flowing through the pipes, exchanging energy with the surrounding ground, which is basically a thermal resistance calculation. And of course, we also need to consider the pressure drops in the pipes, because this will tell us how much pumping power we need to expend. For the design, as with all system designs, we need energy data. We need energy per month, the kilowatt hours of heating, cooling, and domestic hot water. We need capacity data, the peak load capacity in kilowatts and the duration in hours. And also we need information about the heat pump that's going to be applied. We need to know what the efficiency is at different temperatures, for instance, temperatures for space heating and for domestic hot water production. And perhaps we need to know something about how cooling is going to be done, whether that is passive or using the heat pump itself. And as we discussed before, the soil thermal parameters. Now we will focus on the calculation methodology, and in module 1.2 we introduced fundamental methodology used for ground heat exchanger calculations, where the thermal interaction, the thermal response of the soil is important, and we have to consider a very long time scale, 10 or 30 years, 40 years, and a very large spatial scale, tens of meters up to 100s of meters. And the basic methodology that was developed is based on the finite line source. And to speed up computations, the finite line source is, let's say, used to calculate a characteristic function for a borehole field, the so-called G function. And with this so-called G function, we can then very quickly calculate the thermal response of a whole ground heat exchanger field. Now, the example here shows the finite line source for a vertical borehole heat exchanger, where we have a line vertically in the ground, and we can integrate over the line point sources, where we can calculate for each point source the temperature effect at a certain distance, integrating over the line to give us the solution for the whole heat exchanger. Then to impose certain boundary conditions at the surface, for instance, a boundary condition of no temperature change, there is a mirror source on the surface that cancels out the actual finite line source in the ground. And as the distance between the point increases, the cancelling effect becomes smaller. So near to the surface, we have a large cancelling effect, and going deeper, the cancelling effect becomes smaller. In this way, we can model a ground heat exchanger with a boundary condition of no temperature change at the surface. The question then is if we can develop these finite line source equations and G functions for the different geometries that we need to consider for the shallow ground heat exchangers. So the horizontal ground heat exchanger G function for slinky and ring collector ground heat exchanger, and the spiral earth basket heat exchanger. Essentially, what we do is to extend the one-dimensional or two-dimensional vertical borehole heat exchanger to 2 dimensions for the slinky ring collector heat exchanger, and to 3 dimensions for the earth basket ground heat exchanger. So for the slinky or ring collector ground heat exchanger, we get a picture something like this, where in the ground we have the rings at a certain depth from the surface, and we can have mirror rings above the surface at a height that is equivalent to the depth that the rings are buried under the surface. We can then define the finite line source equation for these rings and use them to calculate equivalent G function for a ring collector heat exchanger. This is all detailed in the paper below by Xiong, Fisher, and Spittler 2015, where they developed and validated a ring collector heat exchanger model. For the three-dimensional case, it becomes slightly more complex. We've only drawn one earth basket or spiral ring collector here, but obviously there can be more in the same space at a certain distance from each other. But we now try to model this as a stack of rings where we use the fundamental equation for the rings, but now not in 2 dimensions, but in 3 dimensions. This was developed by Main in a European project called GeoFit and has been validated by laboratory experiments where a computational fluids dynamic model was constructed using laboratory data on the performance of a spiral heat exchanger. This was then extended to be able to compare it with a finite line source approach. The computational fluid dynamics was done in ANSYS Fluent, and you can see in the little table on the bottom left that for different heat injection rates and different thermal conductivities, the root mean square error is in all cases relatively small, especially if we move away a little bit from the actual rings. Again, this was part of the GeoFit project and has been published.